Okay, in my last lecture, I gave you the concept of absolute configuration, how to assign absolute configuration to a stereogenic center, and the nomenclature system that was earlier used was capital D, capital L, that is the DL system, and which was later on replaced by a more robust system, universal system, which is called the RS nomenclature system or the Kahn-Ingold Prelog system, CIP system. Okay. Now, some more concepts on this RS nomenclature system. It has been found that there are some compounds where there is no chiral center, that means a carbon attached to 4 different groups, they are not present, but they are chiral. So, they can exist in enantiomeric forms. So, how to assign the absolute configuration in that case, because you do not have a carbon atom with 4 different groups, so that you can assign the priority order to all these 4 ligands. Now, example of such molecules are, we will not discuss, there are so many molecules which in spite of not having any chiral center in the classical sense, but still they are optically active. For some of those compounds belong to the class of what is called allene, the cumulated double bond system, and another class is what are called biphenyls. Yesterday I told you about the atropisomerism in biphenyl systems. So, we will discuss that when these become optically active, when these become chiral, that then how to assign the configuration of these molecules. Okay. Now, in allene you have the terminal carbons, you have 2 groups, and suppose this is group A and a group B, and interestingly the other 2 bonds in those 2 bonds are written as normal lines. So, that means they are lying in the plane of the board. If you do that, then the other 2 bonds do not lie in the plane of the board, actually both are, one is above the plane of the board at 90 degrees to the plane of the board, and the other substituent B that goes back, and that is also 90 degree to the plane of the board. That means, A and B on this side is occupying a plane which is perpendicular to the plane occupied by the groups on the other side. And the condition for chirality of this type of molecules, allene molecules, is that A should not be equal to B. This is the condition for chirality. That means, at the 2 ends the groups should not be the same. You can notice that the groups on this carbon and the group on this carbon, they are attached to the same groups, but still they are chiral, because the chirality restriction is that on one side the terminal groups A and B should not be the same. If they become same, then there exists a plane of symmetry in this molecule. Now, our problem is, this is chiral, I can show you the model. Actually, the allene looks like this. It is a, so the middle carbon is sp hybridized, and it looks like this. So, you see these 2 bonds are now in a vertical plane, and these 2 bonds in the horizontal plane. And what happens earlier, if they become equal, identical, then there exists a plane of symmetry going through this carbon carbon axis and containing these 2 bonds. Okay. So, the moment one side has 2 identical groups, a plane of symmetry immediately comes and destroys the chirality. Now, we are dealing with a molecule of allene where that is chiral, that means these 2 are different, Okay. How to, because that can exist, because it is chiral, now it can exist in 2 forms, 2 enantiomeric forms. So, how to assign RS configuration to this allene system? So, let us do that. So, the rule says that you stand on any side, either this side or that side, you look at this allene molecule from this side. Suppose I look from this side and I am standing in the plane of the board looking at this molecule with my face towards this carbon-carbon axis. Okay. Now, if I do that, then what happens? This AB, that is the front carbon, attached to the carbon which is facing me towards or nearer to me, and this carbon is the furthest to me. And this A and B will form now a horizontal line. If you take a projection now, so as if they will form a horizontal line, I can show you again. So, what I am saying that I am standing like so, this is the molecule and I am standing like this, and these two bonds, if I take a projection, that will make a horizontal line, and these two bonds will make a vertical line. If I think of the plane here, so you have a back projection from this side, you have a front projection from this side. So, they will again look like a cross, but the cross now, the horizontal bonds, these horizontal bonds are darkened because they are facing the observer, that is suppose me, I am standing here, and this is these two forms the vertical, because this is going towards my head and this is going towards my leg. So, where are these groups now? So, I can place it that this is the A group will be towards my right hand and B will be towards my left hand, and this A will be towards my head and this B will be towards my leg at the bottom. Okay. So, now in order to assign RS configuration, what you do, because I am seeing it from this side, the rule says that the front groups precedes the rear groups. That means the groups at the back. So, if you apply this rule, it means that because you are looking from this side, so these A and B will take higher precedence because they are the front groups than these groups A and B, because they are in the rear position. Okay. Now, suppose your A is number 1, A has a higher atomic number by priority sequence. So, suppose this A is number 1 and this B will be number 2, and then this will be number 3 and this will be number 4. So, you can place these numbers here. So, this A will be number 1, B will be number 2, this A will be number 3 and this will be number 4, because these A, B's are at the rear position. These are 1, 2 because they are in the front, position. So, now you see what is the sequence if you go from 1 to 2 to 3. So, basically you are going from 1 to 2 to 3. So, this gives R configuration. This molecule thus exists in the R configuration. So, let us now go to the actual examples where these A and B's are replaced by groups. They can be different, they can be same. The only restriction for chirality is that at the ends the groups should not be identical. Okay. So, let us take an example of an allene which exists in chiral forms, and we want to do it like suppose this is fluorine and this is hydrogen, and what is whether it is R or S. So, what you do, Now, you can see from this side also, you can practice at home and you see the same result will come. So, if I see from there, again I repeat, I am standing here in the plane of the board. So, my head is pointing towards the methyl and my leg is pointing towards the chlorine, but the horizontal axis is this belonging to the fluorine and hydrogen. So, when I look this from that direction, so that becomes, this is the horizontal axis, and now just to show that this is at the back, the vertical axis, we do this break, so that it looks like that is behind the front line. And now, if you, so these will now, we first have to decide the priority sequence of these two. So, this is 1 and that is 2, and in this case this is 1, this is now this is 3 and this is 4. Okay. So, the projection formula will look like that 1 goes to the right, 2 goes to the left, and then 3 goes to the bottom and 4 goes to the top. Now, you see the sequence of going from 1 to 2 to 3. So, 1 to 2 to 3 is S. So, this molecule is having S configuration. Okay. That is in case of alene. Again, you should practice by seeing from this side, but the result should be same, it does not matter. Only thing, if you see from this side, then this will become 1, that will become 2, this will become 3, that will become 4, that you have to remember. And also remember that this is not a Fischer projection formula. The fourth group here is always away from you, because the moment you start seeing from here, the fourth group will be on this side, and that axis, that line will be always behind the front line. So, the fourth group will occupy the back line. So, it is always behind you, it does not matter whether it is in the horizontal or in the vertical axis. Okay. It is always at the back. So, you do not have to think over it, that whether in Fischer projection you have to be careful that the fourth group is occupying the horizontal or the vertical position, but here you do not have to bother about that, because the fourth group is always away from the observer, even if it is occupying a horizontal position. For biphenyl system, which are called also which can exhibit atropisomerism, but not the simple biphenyl. Here what happens, that if you put some groups at the ortho positions, at the two ortho positions, so if you put groups here A and B, and here A and B, and if the groups are not hydrogens, they are bulky groups, then there will be steric repulsion if the two rings remain in the same plane. So, if you draw it in the same plane, they remain, then there will be steric repulsion between. So, this is B, this is A. So, now this hits the other group B. So, in order to reduce that steric repulsion, so what is the benefit of having these two rings in plane? That you have extended conjugation between the two benzene rings, but while doing so, there is huge steric crowding that is affecting the stability of the molecule. And in that case, to reduce that steric compression, one ring rotates and ultimately the two rings become orthogonal to each other. Okay. And as they become orthogonal to each other, earlier what happens, there was a plane of symmetry. I told you once that all planar molecules have a plane of symmetry. It is the plane of the molecule that is the plane of symmetry. So, they are all achiral, but the moment it becomes non-planar, that this is in the plane and this is orthogonal to the plane of the board. So, it becomes a there is a possibility of chirality now. Now, again the condition is similar, that A should not be equal to B, but it does not matter whether there is no restriction whether this is same as this or not. That is not the question. The important thing that you should look, that whether the groups at the ortho position of a particular ring are they different in both the rings. If that is the case, then that becomes a chiral molecule. Now, again how to assign, because this is a chiral molecule, if A is not equal to B, then there is a question of assigning the absolute configuration, because this can exist in another form, which is an enantiomer, the mirror image of this. So, in this case also what you do, you look from one side, suppose I am looking from this side and I am standing, my head is again, I am standing in the plane of the board. So, plane of the board, I am looking from this side. Okay. So, if I do that, then this benzene ring will form a horizontal axis, and which is, because it is closer to me. So, I put it like this. So, I am considering this part, the whole part, which is attached with this AB groups, and I am looking at this carbon-carbon axis. So, I am looking to the carbon-carbon axis, and now take a projection of this part and that part. So, if I do that, this will form a horizon, this vertical line, vertical projection line, but I make it bold because that is closer to me than this part, which also forms a line, but that goes behind the vertical line. So, just to show that, I make a break here, that this is in front. So, that is actually shadowing the portion of the line here, you cannot see that line. So, this is the scenario. Now, we have to put the now you apply the same rule, that the groups which are in the front, which they will the front groups will be awarded higher priority than the groups at the back. Okay. And if you do that, then what happens? This is, you look at this, this is, suppose this is 1 by priority sequence, this is 2, and now this should be 3 and this should be 4. So, you now convert it, this should be your 2 and this should be your 1, this should be your, so now that goes to your left side A, the number 3, and that should go to your right side. So, if you do that, then 1 to 2 to 3 is clockwise, and that becomes, sorry, this becomes S, anti-clockwise. This is anti-clockwise, 1 to 2 to 3, that is anti-clockwise. So, this is a S molecule. Okay. So, this is the way you assign absolute configuration to systems where there is no conventional chiral center present. Okay. The rule is that the front groups precedes the groups at the back. Okay. So, this is the rule, sometimes called, this is the rule 0. Yesterday I did not mention about this rule, because at that time we were not exposed to these systems where there is no classical chiral center present in the molecule. Okay. Now, in case of, I did not tell you about the assignment that is made for the double bond, but that is really very easy. Instead of cis and trans, these are replaced by E and Z, and E and Z are basically, what happens is for a double bond, which can exhibit isomerism. So, if you have a double bond like this, and if you have, suppose, a methyl, a hydrogen and fluorine and chlorine, suppose this is the configuration of an alkene, then its geometry is the problem, you see the cis and trans. Now, you cannot apply the cis and trans configurational nomenclature to this system. So, instead what you do, you assigned, you see two groups here, attached to one sp2 carbon and 2 groups here attached to another sp2 carbon. So, we assign the priority sequence between these two groups separately and assign the priority sequence between these two groups separately. So, if you do that, so this becomes 1, this becomes 2, and here this is 1 and this is 2. So, now what we are saying that these two top priority groups are anti to each other, are trans to each other, and that is what is called a Z configuration. And the other molecule, that means, if you have methyl here, hydrogen there, and chlorine here, fluorine there. So, here now this is 1, this is 2, this is 1 and that is 2. Now, the top priority groups are on the same side. So, in the classical sense they are cis to each other, and this is what is called the sorry, I am sorry, extremely sorry. This is the E configuration and this is the Z configuration, it is the other way around. So, Z is the system where the two groups are on the same side, and E is the system where the groups of same priority are trans to each other. Okay. So, this is the Ez, and you remember the RS rule that cis precedes trans. So, if you have a scenario where you have to decide the priority between cis and trans, then cis precedes trans. That means, so here the rule will become Z. So, it is like a cis system, 1 groups at the same side, Z precedes E. Okay. Okay, so, that is the configuration of double bond systems. I should also mention one thing, that these alene molecules or the biphenyl molecules, the isomerism in biphenyls have a special name, atrophy isomerism, but since they do not have the classical chiral center, what they have is what is called a chiral axis, and that is why they are called axially chiral molecules. Okay. Because along the axis in tetrahedral carbon, what happens that tetrahedral carbon, the classical stereogenic center, now it is called stereogenic center, earlier chiral center. Let us stick to the, suppose the classical definition. So, here what happens that all the 4 groups are attached to a single carbon, and if you interchange any of these 2 groups, suppose this is X, this is Y, this is Z and this is P. If you interchange the position of X and Y, you get a stereoisomer. Okay. In case of alene or biphenyl, what happens? You have an axis. In case of an alene, you have an axis going through the carbon, 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 all the 3 carbons, and now groups are arranged in this fashion. So, here what happens that if you interchange the position, very similar, but it is the axis now. If you interchange the position of X and Y, you get the other isomer. So, these are called axially chiral molecules. One more concept I think we should also tell, that suppose I have a system like this, where there are 3 wedges and this molecule I ask you to assign the configuration here. Now, first of all, it looks little bit awkward, because this molecule is not a chiral molecule. this molecule is not a chiral molecule because it has got a plane of symmetry. However, if you look at this carbon is a stereogenic center, because if you interchange that position of that carbon, you get another mesoisomer, but that is a different one from the starting. So, this carbon is a stereogenic carbon. This carbon is also stereogenic. So, all these carbons are actually stereogenic. If you interchange, you get other types of isomers. So, now let us see, if I want to assign the configuration of this carbon in this molecule. So, what I do? I have 4 ligands, one is OH, another is hydrogen, here a big ligand, and here there is another big ligand. Okay. If these 2 ligands, now these 2 ligands are little bit different from the cases that we have discussed earlier. These ligands have an inbuilt chiral center. So, there is a chiral center, although they are constitutionally same, but we have to be careful. We have to see what is the configuration here, what is the configuration here. That means, what is, whether it is R or S or whether this is R or S. If both are R, then the chiral this is no longer a chiral center, because both the 2 hands are same. So, let us do first. So, in order to do the absolute configuration of this carbon, you have to do the absolute configuration first of this carbon. So, what you do, this is 1 for this carbon, this will be 2 at the back, this will be 3 at the front, 1, 2, 3, but the hydrogen, remember, is on the horizontal side. So, what you see, you just reverse it, that means 1, 2, 3 you are looking clockwise, but actually this will be S. Similarly, if you do that, this is 1, this is 2 for this carbon and this is 3. So, this looks like anti-clockwise, but actually hydrogen is on the horizontal line. So, this is R. So, that means these 2 groups have different configuration. So, now you assign the priority sequence of the ligands attached to this carbon. So, this carbon, this is OH. So, that must be, now I erase this just to avoid complexity. So, this is your first group, number 1. Now, the rule says R precedes S. So, that means this is your number 2 group and this is your number 3 group, this is the hydrogen, that is number 4 group. Remember, hydrogen is in the horizontal side. So, now 1 to 2 to 3, what you do? You just see what is the result here, 1, 2 to 3. It looks like that it is going in a clockwise sense, but since the hydrogen is occupying the horizontal line, so it should be the other way around. The absolute configuration will be S. Okay. So, this will be S. So, this molecule is actually SSR. Now, interestingly, so this molecule, accordingly you can tell that what it will be, because this still remains S, because you have changed only this carbon, this remains R, only this one got changed. So, that must be having a R configuration. So, this is SSR and this is SRR, and the plane of symmetry is still there, because we know that S is the mirror image of R. So, there is a plane of symmetry here, there is a plane of symmetry here, S is the mirror image of the R. Okay. Now, if you just draw a similar a molecule with similar constitution, but with stereochemistry little different, like this OH is here, that OH is there, and the top the down OH you put on the at the bottom, and then see what happens now. Without going into the priority sequence, we can tell, because this carbon remains the same. So, this is S, and this carbon I have actually interchanged the position of the groups. So, that will now, earlier it was R, now it should be S, now it should be S. So, these 2 are S. So, this carbon now is no longer a chiral center. Earlier it was chiral, when these in the mesophore, when these 2 OHs are on the both side, on the same side, but when they are on the opposite side, now it is no longer a chiral center or asymmetric center. Okay. So, that is why this type of carbon is what is known as, because it is sometimes asymmetrics or chiral, or sometimes it is not. That depends, the chirality of this center depends on the asymmetric absolute configuration of the adjacent asymmetric center. So, this is classically named as pseudo asymmetric center. Okay. So, this was the concept. So, that is, you see the same carbon in different environments can behave as a chiral center and may not be a chiral center. That is why the name is a pseudo chiral center. So, sometimes chiral, sometimes not. Okay. So, I think this clears some of the it just an extension of the earlier concepts. So, what we have done, that first we have done the absolute configuration assignment of molecules which do not have a chiral center in the classical sense, like allenes and biphenyls, and then we introduce the concept of pseudo asymmetric center and how to assign configuration of molecules where there are the same chiral centers are present, but they are in different configuration. Okay. And also we have done the Ez, how to assign Ez configuration in the double bond systems. Okay. Thank you.